Lesson 941, Confidence Intervals and Hypothesis Tests for Independent Samples. Suppose you want to estimate the difference between the mean commute time of students at your college and the mean commute time of faculty at your college. To carry out this study, you gather two random samples. One sample is from the students and one sample is from the faculty. Your samples give you the following sample statistics. Commute times are in minutes. So in this table we have two important columns, sample 1 and sample 2. Sample 1 is students, sample 2 is faculty. And then we have these rows, the mean for both students, the sample standard deviation for both samples, and the sample size for both samples. So for the students, the mean commute time is 35.5 minutes, the standard deviation is 10.60 minutes, and the sample size is 45. For the faculty, the mean commute time is 46.2 minutes, the sample standard deviation for the faculty is 8.60 minutes, and the sample size for the faculty is 35. Number 1, are the samples independent? If yes, what makes the samples independent? If not, why not? The question about independent is, can someone be a student and faculty at the exact same time? And we would answer no to that. So the samples are independent. Because students and faculty are two different groups of people. Number 2, look at the sample table. Which sample has the longer average commute? If we're talking about average, then we are talking about mean, and the larger mean comes from the faculty, which had an average or mean commute time of 46.2 minutes. Now calculate the difference in sample means, x bar 1 minus x bar 2. Let x bar 1 be the sample mean commute time for the students, coming from sample 1, and let x bar 2 be the sample mean commute time for the faculty, coming from sample 2. The value x bar 1 minus x bar 2 is called a difference of sample means. That's all that is. Explain how the sign of the difference, positive or negative, tells us which sample mean is greater. So first of all, if we calculate the difference of sample means, that would just be the mean for the students, 35.5, minus the mean for the faculty, 46.2, which would give us negative 10.7 minutes. In this case, we get a negative. So how does this tell us which sample mean is greater? Since it's negative, the second sample mean is greater, which we can obviously see because 46.2 is greater than 35.5. Next steps. Our goal is to use differences of sample means to make inferences about the difference in population means. In order to do this, we first must understand the center, the variability, and the shape of the sampling distribution of all statistics of the form x bar 1 minus x bar 2. So we're going to take a look at the sampling distribution of differences in sample means. Suppose two sample means are computed from randomly selected samples of two populations. Typically, we do not know the standard deviation of either population. What we need to know is that the criteria for normality are met for each sampling distribution of sample means. That is, we need to know that either the populations are normal or the sample sizes are greater than 30. That's our criteria. We want to construct confidence intervals and test claims about the difference of two population means. To do this, we must first understand the distribution of differences of sample means. In Module 8, we discovered a very important fact regarding differences in sample proportions. Differences in sample proportions, if the two sampling distributions of sample proportions are approximately normal, then the sampling distribution of differences in the sample proportions is approximately normal as well. This fact turns out to be true in this module for sample means. For differences of sample means, if two sampling distributions of sample means are approximately normal, this occurs when our criteria is met, sample size is greater than 30, or the population is normal, then the sampling distribution of differences in sample means is approximately normal as well. Also in Module 8, we learned that the mean of all differences in sample proportions is equal to the difference in population proportions. A similar result is true for the distribution of all differences in sample means x bar 1 minus x bar 2. So we see this whole conversation summarized in another one of those very important you need to know boxes. Just as a reminder, if there's a box that says you need to know, then that is something that you need to know. So here's what we need to know for this lesson. A sampling distribution of differences in sample means is the distribution of all possible values of x bar 1 minus x bar 2. The sampling distribution of differences in sample means is also known as the sampling distribution of those differences, x bar 1 minus x bar 2. When two populations are independent, the mean of the sampling distribution, x bar 1 minus x bar 2, is equal to the difference in the population means, mu1 minus mu2. So this is saying something very important. The mean of the sampling distribution of x bar 1 minus x bar 2, that is just the difference in population means, mu1 minus mu2. The standard error, something else that we need, of the differences in sample means is given by this formula. The standard error of differences is the square root of, and if we zoom in on this, two fractions. The first fraction has sigma sub 1 squared divided by n1. And when we see that, sigma stood for population standard deviation, but when we square it, that gives us the variance. So it's the variance for sample 1, or population 1 I should say, divided by sample size 1, plus the variance for population 2 divided by sample size 2. Recognizing that the population standard deviations will likely be unknown, we estimate the standard error using sample standard deviations. So notice this next standard error is a estimated standard error, and it has the same formula. It's a square root of the sum of two fractions, but now we have the variance for sample 1 divided by sample size 1 plus the variance for sample 2 divided by sample size 2. As always, the margin of error is equal to a critical value multiplied by the standard error. With sample standard deviations used in place of population standard deviation, we are forced to use t critical values. So here's our margin of error, again capital E. That's equal to a critical value, t sub c, times this same square root that we had for our estimated standard error. The correct value for the degrees of freedom for such an application of the t distribution is unclear, with two sample standard deviations used in the standard error. The use of the estimated standard error above in standardizing differences of sample means creates a test statistic which is distributed approximately according to a t distribution. Unfortunately, the degrees of freedom for this application are quite complicated. Because of this complication, we will provide degrees of freedom for you, meaning in the take-it-homes, in the checks, and in the exams, we will be providing the degrees of freedom for this particular example. With the margin of error computed, then as we've done before, the difference of the sample means x bar minus x bar 2 is the point estimate for the difference of population means, and the corresponding confidence interval is the same as we've seen before. Take your point estimate and then plus or minus your margin of error. So you have your point estimate minus the margin of error, comma, the point estimate plus the margin of error. So this is just like we saw in Module 8. So for constructing confidence intervals, number 4, using the sample statistics from Table 1 above, that was on the first page of this lesson, answer the following questions. So first, determine the estimated standard error for the sampling distribution of differences in sample means. So the estimated standard error formula that we saw before was equal to the square root of, and again, if you just turn to the previous page, you have S1 squared divided by N1 plus S2 squared divided by N2. So I'm going to take the information that was from the table on the first page of this lesson. We had that S1, the standard deviation for sample 1 was 10.60 minutes. So I'm going to take 10.6 and I'm going to square that and then divide by N1, which was 45. And then I have to take the standard deviation for the second sample, which was 8.60. So 8.6 squared, and then divide that by the sample size for sample 2, which was 35. All right, now this is going to take a lot to put into the calculator at once. So I don't recommend doing that. It is okay to break this up into steps. So for example, if I just focus on that first fraction, 10.6 squared divided by 45. That would give me 2.496889. I'm not rounding too early because I'm in the middle of a calculation, and I can do the same thing with the second fraction, 8.6 squared divided by 35, and that would give me 2.113142. Now I can take the square root of the sum of these two numbers, 2.496889 plus 2.113142. And so then I get approximately, for my answer, 2.147. That becomes my estimated standard error. If you do this all at once, you just need to make sure you're using a lot of parentheses for trying to type that all into your calculator at one time. Part B. Determine the margin of error for a 95% confidence interval for the difference of population means. The degrees of freedom for the t critical value are 77. So in this case, they gave us the degrees of freedom, 77. They also gave us the 95% confidence level, and we want the margin of error, which means E equal to the critical value, T sub C, times that estimated standard error. And I'm not going to write the formula out for the estimated standard error because I already did that in Part A. So there is a table that we can get these critical values from. We've seen that before in previous lessons. In the case of when you see a problem like this on the take it home or the check or on the exam, we would have that table for you. So I have already gotten that critical value from the table. It is 1.991, and the estimated standard error that we had from Part A is 2.147. And when I multiply those two numbers, I'm going to get approximately 4.275. And again, just as a note for when you're looking at this later, this will be provided, or we can find it from a table. I would just say go back to the previous lessons in Module 9 and remember where we had those tables of those t sub c values before. That's where I got that from. So now part C. Construct a 95% confidence interval for the difference of population means. So again, this would be x bar 1 minus x bar 2 minus the margin of error, comma, x bar 1 minus x bar 2 plus the margin of error. We already had the difference of these sample means before from the first page of this lesson. That was negative 10.7. And then I have to subtract the margin of error, 4.275. And then I also have to take negative 10.7 and add 4.275. And so what I get for my confidence interval is negative 14.975, comma, negative 6.425. That is my confidence interval. So now we get to some interpretations. Part D. Does the confidence interval that you constructed in question 4C, so the answer we just boxed, does that allow for the population means to be equal? The way that we can answer this is if the population means are equal, then their difference would be 0. So if they are equal, the difference would be 0. The confidence intervals that we build are trying to estimate these differences. So in that confidence interval, is the estimation of 0 possible? And we would say no. 0 is not between those two numbers, so this is not possible. So 0 is not in our interval. So we would say no. That's the answer to this question. And the reasoning is 0 is not in the interval. Part E, based on the confidence interval, again, that we had in question 4C, which group, students or faculty, have a lower commute time? So what we can notice is that the confidence interval is estimating all negative differences. So the confidence interval estimates all negative differences. Those are the only possibilities, since we have negative 14.975 up to negative 6.425. So if we only have negative differences, then think back to the first page of this lesson, where we said if we have negative differences, the second sample mean is greater, which means the faculty has a greater commute time. So then what does this confidence interval tell us? It tells us that who has the lower commute time? Students. If faculty are greater, then students are lower. So those are two interpretations we can do for our confidence interval. These are questions we've seen before in other contexts. So now question 5. In question 4C, you constructed a confidence interval. Now interpret the confidence interval. We're going to do this just like we've seen in other contexts. This interpretation should include our confidence level, what it is we are confident about, and the mean commute time information. So we want to talk about the difference in mean commute times here. So first of all, our confidence level was 95%. So we are 95% confident that, and now we need to state what it is that we are confident about. So we are 95% confident that the mean commute time for all students is between 14.975 minutes and 6.43 minutes. And now here we need to make a distinct indication that we're talking about a difference. So we are saying that the students have a lower commute time, so these minutes are less than the mean commute time for faculty. So notice we took the idea that the commute times for students were lower, and we included that in our conclusion by having this word less. The numbers that we used, we didn't use the negatives because, again, the negative is implied with the word less. So these are minutes below the mean commute time for all faculty. We could have also written a summary that said something about the difference in mean commute time, but this conclusion here makes a little bit more sense when you're talking about the students have a lower commute time, and here's about how many minutes it is lower than for faculty. So that's looking at confidence intervals. Now let's move on and look at hypothesis tests for these same things, the difference of population means. When we are testing a claim about the difference in two population means using independent samples, the hypothesis testing process is similar to those in previous lessons. Step 1, determine the hypotheses. The null hypothesis states that the difference between the two population means is 0. This is the same as saying that the population means are equal. So this is just like what we saw in Module 8 with proportions, but now we are looking at means. So either the two population means are equal or the difference between the two population means is 0. So that's why we see our null hypothesis stated h sub 0 colon mu1 minus mu2 equals 0, or we could say h sub 0 is mu1 equal to mu2. The alternative hypothesis will be one of the following inequalities. Just like we've seen before, it's almost the same statement as the null hypothesis, but we're going to have some sort of inequality. So either mu1 minus mu2 is less than 0, which also means the same thing as mu1 less than mu2. That's a left-tailed test. We could have mu1 minus mu2 is greater than 0, which means the same thing as mu1 greater than mu2. That's a right-tailed test. And then mu1 minus mu2 is not equal to 0. That's the same thing as mu1 not equal to mu2. That's a two-tailed test. So this is very similar to what we saw in Module 8, just different symbols. We don't have P1 and P2. We have mu1 and mu2, standing for population means. After we state our hypotheses, we have to collect the data. We must verify that the criteria for the approximate normality of the sampling distributions are met. The criteria are each population must be normal or the sample sizes must be greater than 30. It's exactly like what we've been seeing for a few lessons now. For this lesson, the samples must be independent. The values in the first sample cannot have any influence on the outcome of the values in the second. And then the samples must be randomly selected from the populations. Once the samples have been collected, we need to compute the following: the mean of each sample, the standard deviation of each sample, and the difference in the sample means. After we've done all that, then we can assess the evidence. If the null hypothesis is true, the sampling distribution of differences of sample means will have the following parameters. We're going to have that the mean is mu1 minus mu2 equal to 0. This is something that we're going to use in a formula a little bit later on. We also have the standard error, just like we've seen before. the square root of s1 squared divided by n1 plus s2 squared divided by n2. The test statistic is given by the formula capital T for our T statistic. Here we see the difference in sample means minus the difference in population means divided by the standard error. But also notice that since we have the mean, mu1 minus mu2 is equal to 0, this comes from our null hypothesis. Then subtracting that just means we're really subtracting 0, which is why really that T formula just becomes this simplified version. Since we are using the sample standard deviations to estimate the standard error, the test statistic varies approximately according to a student's T distribution. Recall that you will be given the degrees of freedom, and you're also going to be provided with a table of T-scores, or maybe even provided with that also. We're going to assume that the null hypothesis is true. When the null hypothesis is true, the p-value is the probability of observing a random difference of sample means that is at least as extreme as the one observed. This is a reminder of how we've interpreted p-value in the previous two modules. We will use technology or tables to find the p-values. This is just like what we saw over the last couple lessons. We're going to use TCDF or the t-test. Finding the p-value. For a left-tailed test, the p-value is the area to the left of the test statistic. For a right-tailed test, the p-value is the area to the right of a test statistic. And then for a two-tailed test, the p-value is twice the area to the right of a positive test statistic, or it is twice the area to the left of a negative test statistic. This is all review right here. And then finally, step 4, state a conclusion. Finish the hypothesis test by presenting a complete conclusion with the following items. Do you reject or fail to reject the null hypothesis? Does the data support or not support the alternative hypothesis? State what your p-value is or your level of significance, and then write a conclusion in context of the whole situation. So to finish this lesson, let's look at an example. Imagine that a community college math department uses the same final exam for all college algebra students. The department chair is concerned that students in online courses do not do as well as students in on-site courses, meaning courses in which the students are in the classroom. The fundamental or basic research question here is, do students who take online courses perform poorly by comparison to students in on-site courses? So we can think of this as a claim, or we can think of this as something that we are trying to reach a conclusion about. So to reach a conclusion about that question, the instructor takes a random sample of 40 on-site students and 35 online students. She finds the final exam score for each student in the random sample. The mean score for the on-site students is 75 with a standard deviation of 12. The mean score for the online students is 72 with a standard deviation of 15. Conduct a test at the 5% significance level to determine if the mean score for all on-site students is higher than the mean score for all online students. So just to think about this situation, notice that she doesn't have all students here, just a sample, 40 on-site and 35 online. The on-site students got a mean score of 75, and the mean score for the online students is 72. So it looks like the on-site students have a higher mean score than the online, but again, this is just for a sample. And 75 is greater than 72, but is it significantly greater? So again, this is the question. We're trying to see if this is a significant difference. So number 6, the on-site students are population 1, and the online students are population 2. What are the null and alternative hypotheses? So, our null hypothesis would be mu1 minus mu2 equal to 0. Or we could say that mu1 is equal to mu2, meaning the mean score for the on-site students is equal to the mean score for the online students. For the alternative hypothesis, Remember that the question was, do the students who take online courses perform poorly by comparison? Poorly would mean they have a lower score. Online less than on-site. If the online has less scores than the on-site, that means that the on-site students have higher scores, so they are greater. So the on-site students, their mean score, mu1, should be greater than mu2, which also means the same thing as their difference, mu1 minus mu2, is greater than 0. This one took a little bit to unpack because the question compared them in an opposite order, but just think if one is less than the other, then the other has to be greater than the first one. That's what we have here. mu1 is greater than mu2. Is this a left-tailed, right-tailed, or two-tailed test? These are always easy questions to answer. It just comes straight from your alternative hypothesis. That inequality, you can think that is essentially pointing to the right, so that is a right-tailed test. Step 2, collect the data. Number 8, we saw earlier in the lesson that the sampling distribution of differences in sample means is approximately normal when the individual sampling distributions of sample means are approximately normal. Does each sampling distribution meet the approximate normality criteria? So the first thing we can check is, are the sample sizes greater than 30? If we go back to the first page, we will remember that the sample size for Step 2, collect the data. Number 8, we saw earlier in the lesson that the sampling distribution of differences in sample means is approximately normal when the individual sampling distributions of sample means are approximately normal. Does each sampling distribution meet the approximate normality criteria? So the first thing we can check is sample size. And if we go back to what we were given, we have a sample for on-site students is 40, and the sample size for online students is 35. Both of those are greater than 30. So we can at least just stop there and say yes, since both sample size are greater than 30. Are the samples independent? How do you know? No student would take the same class twice, so anyone who is taking the class online would definitely be independent from anyone who is taking the class on site. So we would say yes, 2 different classes. Each student would only take 1 class. Number 10, calculate the difference of the sample means. So notice here we were already given the sample means. So we need to take the mean for sample 1, and that would come from the on-site students. So the mean score for on-site students is 75. The mean score for online students was 72, and that difference is 3. Number 11, look at your alternative hypothesis. Is the difference of the sample means consistent with your alternative hypothesis? Meaning, the difference that we just found, 3, does it agree with what we wrote in our alternative hypothesis? And if we notice, the difference that we got is greater than 0. 3 is greater than 0. So here's my hint to you. This is a good way to check that your alternative hypothesis was written correctly. If you would have written mu1 minus mu2 is less than 0, then this wouldn't agree. which if you were running this sample and they didn't agree, then you might think, well, I didn't even gather any good information. But what this is really doing is just checking that you wrote down that alternative hypothesis correctly. Step 3, assess the evidence. Number 12, calculate the test statistic for your observed difference of sample means. So again, we saw that the test statistic would be this very complicated fraction, parentheses x bar 1 minus x bar 2 minus mu 1 minus mu 2 in the numerator divided by the square root of s1 squared divided by n1 plus s2 squared divided by n2. We can put some things in from what we've already calculated. We already have x bar 1 minus x bar 2 is 3. We already have from the null hypothesis mu 1 minus mu 2 is 0. And then under the square root, we can take our standard deviation for sample 1, which was given as 12 squared divided by sample size 1, which is 40. And then plus the standard deviation for sample 2, which was 15 squared divided by 35. If we want to break up some of the work, you could add those two fractions. So if you use parentheses 12 squared divided by 40 plus another set of parentheses 15 squared divided by 35, this would give you under the square root, I haven't done that yet, 10.028571. And now I can just type 3 divided by the square root of 10.028571. And now I can round my final answer to 3 decimal places, 0.947. That is my t-test statistic. So now number 13, sketch the t-distribution. Identify the position of the observed test statistic and shade the area that represents the p-value. This is just like we've seen before. I have a horizontal axis. I have something that looks like an approximate bell shape. I've got a t statistic that is on the right because it is positive, t equal to 0.947. We have a right-tailed test, so the p-value is the area shaded to the right. And then finally, number 14, find the p-value. In this example, there are 64 degrees of freedom for the t-distribution. So we're going to find this p-value just like we did before, second, vars, and then tcdf on our TI-84. You have to put in your lower t-score, which for a right-tail test would be our t-score 0.947. Comma the upper t-score, which would be 1e99, because we are going to the right, positive infinity, comma the degrees of freedom, which we were just given that, and again, we will be given that in other problems. Plugging that into our calculator, we should get approximately 0.174. The secret word is t-distribution. So now step 4, finally our conclusions. Number 15, how does the p-value compare to the significance level? Our p-value is what we just calculated, 0.174. If we go back to the beginning of this example, we saw that our significance level was 5%, which is 0.05. So alpha equals 0.05. And we see that our p-value is greater than alpha, just by comparing those two numbers. So since we have the p-value is greater than the significance level, this tells us to fail to reject the null hypothesis. So if we fail to reject the null hypothesis, as we've seen in some examples from just the prior lessons, the data does not support the alternative hypothesis. That's our answer for number 16. So if we go back to our hypotheses, our data is supporting the alternative hypothesis, which states that the online students are not doing as well as the on-site students. But that's not supported, which means that the question we had, do students who take online courses perform poorly by comparison to students in on-site courses? No, the data does not support that conclusion. So, in our conclusion that we want for number 17, we can say at a 5% significance, the data does not suggest that the online students perform poorly when compared to on-site students. The data does not suggest that the online students perform poorly when compared to on-site students. There is a difference in those sample mean scores, but it isn't that significant of a difference. So that data does not suggest that one is doing differently than the other. They're essentially doing the same. So that means the same thing as saying the online students don't seem to be performing poorly when compared to the on-site students.